So today we are learning about the most important and quite repeated type of questions do occur from this concept called as hydrogen bonding. So what is the criteria that hydrogen bonding could happen? The first thing is that the hydrogen should have bonded with more electronegative atom. So ma'am, I'm having water. Here you could see this hydrogen is bonded with more electronegative element. Similarly, this hydrogen is also bonded with more electronegative element. So these two hydrogens are eligible to do hydrogen bonding. Okay. Where will it go for hydrogen bonding? Now comes the second criteria. Second criteria is that the lone pair should be present on the more electronegative atom. So this hydrogen is seeking for the hydrogen bonding with some other element. Let me say it's NH3. Here it could go for hydrogen bonding because nitrogen is an electronegative element. First check. Second check, does it have lone pair of electron? Yes, it has lone pair of electron. In that cases, hydrogen bonding can happen. And the element with which the hydrogen goes for this bonding, this element should be smaller in size. That is also very important. Not just because it is having lone pair, it can go. They should be smaller in size as well. So three important criteria we have to check to look for hydrogen bonding here. Check number one, whether the hydrogen is bonded with more electronegative element. Number two, the element to which it is going to get bonded should be having a lone pair and it should be as well more electronegative as well. And number three, that electronegative atom should be smaller in size. So if three conditions are there, then hydrogen bonding is a possibility. So when we look at the hydrogen bonding, three elements usually comes for hydrogen bonding: oxygen, nitrogen, and fluorine. Oxygen, nitrogen, and fluorine. So let us understand the strength of hydrogen bonding here. We're looking for the strength of hydrogen bonding. I'm considering between F, H, F. Hydrogen fluoride, HF molecule. Is the hydrogen bonded with most electronegative element? Yes. Okay. Is the hydrogen getting bonded with an element, electronegative element, which is having lone pair of electron? Yes. It is having lone pair, it is getting bonded. Correct. Is that element small as well? Yes. So the first point is that check whether this hydrogen is bonded with more electronegative elements. Number two, whether that hydrogen is bonded to electronegative element which is carrying lone pair also is smaller in size. If all these checked boxes are filled, then they can manage to make hydrogen bonding. Now let us consider the trend here. Hydrogen is bonded with oxygen, hydrogen bonded with nitrogen, hydrogen bonded with chlorine. Which is more electronegative among them? Oxygen. So this is going to do the effective hydrogen bonding. Okay. Followed by NH, followed by CLH. Now look where the hydrogen is getting bonded. Is it an electronegative element? Yes. Is it electronegative? Yes. Is it also electronegative? Yes. Does it have lone pair? Yes. Does it have lone pair? Yes. Does this have lone pair? Yes. But among them, which is smaller? Oxygen is only smaller. So its effectiveness in making hydrogen bonding is quite significant here. Followed by this. Followed by this. So basically, we can understand the HCl cannot make hydrogen bonding very significantly because chlorine size is larger compared to nitrogen and oxygen. Over.
Yes, ma'am.
Right. Let us consider the strong hydrogen bonding patterns. Among these molecules, which would do stronger hydrogen bonding? Oxygen bonded with most electronegative element. Where is the hydrogen bonded? Here the hydrogen is bonded with carbon. I mentioned hydrogen should be bonded with oxygen, nitrogen or fluorine. Only those hydrogens goes for effective hydrogen bonding. So definitely it can't happen here. Here there is no possibility. There is no hydrogen at all. Now I am having two hydrogen bondings. Hydrogens are available in both the compounds now. Among them, which is more electronegative? Obviously, oxygen, isn't it? So therefore, effective hydrogen bonding, strongest hydrogen bonding, can be made by water. Let's go for the next question now. Where hydrogen bonding is not possible. Consider where is this hydrogen bonded to? Nitrogen, oxygen, fluorine. Are they the electronegative element? Yes. Among them, which is not that much electronegative? Sulfur. So this do not do effective hydrogen bonding. Now when I look at this HF, fluorine being very small, highly electronegative element here, HF generally forms linear zigzag polymer structure. This question where it was repeated most of the times in JEE statement based, HF forms what type of an polymeric structure? Linear zigzag polymeric structure, both in solid as well as in liquid forms. Going for the next question, maximum extent of hydrogen bonding. Where is it possible? Maximum extent. Ma'am, when I'm looking at hydrogen bonding, can H2SE make hydrogen bonding? Akriti, can H2SE make hydrogen bonding, ma?
Um, no, ma'am. I
Nitish,
think it
what do you
has
think?
less electronegativity.
That's right. That's right. H2SE cannot make hydrogen bonding here because of the less electronegativity. What about the another compound that's given there? What about H2S? Can it make hydrogen bonding?
Uh,
Yes, ma'am.
yes, ma'am.
Array, we just now saw this now, which will not form hydrogen bonding. H2S, can it form hydrogen bonding? We, I was oxygen, nitrogen, fluorine. If the hydrogen is bonded with these three elements, only hydrogen bonding is possible. Here
Okay.
also hydrogen bonding is not possible. Here also not possible. Now the question is, HF can also do hydrogen bonding. H2O can also do hydrogen bonding. Now the question is asking you maximum extent of hydrogen bonding. In the case of water, I have two hydrogens that are bonded with oxygen. In the case of HF, only one hydrogen is bonded. So this can also go for hydrogen bonding. This can also go for hydrogen bonding. So the maximum extent here means how many hydrogen bonding is possible with one molecule.
Okay, ma'am.
right? Let's go to the next question. Strength of hydrogen bonding. So we are discussing between the different elements here. Hydrogen bonded with fluorine, hydrogen bonded with oxygen, hydrogen bonded with nitrogen, hydrogen bonded with chlorine. Definitely, it's going to be very less. Comparing them, as I told you already, fluorine is electronegative, it is small in size, and it has lone pair. So it forms superior hydrogen bonding, followed by this, followed by this. Next one, types of hydrogen bonding. There are two different types of hydrogen bonding is possible. Type number one is called as intermolecular hydrogen bonding. Intermolecular hydrogen bonding. The next one is called as intramolecular hydrogen bonding. So the word inter and intra tells us what kind of hydrogen bonding happens. Consider this inter-school competition. That means your school is going to participate with some other schools, isn't it? In same way, intermolecular hydrogen bonding, where the molecule is participating in bonding with another molecule. You understand? Like this.
Yes, ma'am.
Intermolecular hydrogen bonding. Here you can see the bonding is happening with the same molecule itself. So I can say homo intermolecular hydrogen bonding. If the bonding is happening with some other molecule, consider I have NH, water is there, that this hydrogen is bonding with nitrogen of ammonia. This is also hydrogen bonding. But the hydrogen bonding is happening with some other molecule. Then I call this crossed intermolecular hydrogen bonding. The next one is intramolecular hydrogen bonding. Within its own molecule, the bonding is happening. I call this intramolecular hydrogen bonding. Consider I have the molecule that you're seeing right now is called as orthohydroxy benzoic acid. Between OH and carboxylic unit is important unit. So to this, at the very first position, OH is available, which is called as ortho position. Orthohydroxy benzoic acid means carboxylic acid that is attached with benzene. Orthohydroxy benzoic acid. We are looking what type of bonding is possible here. Here you can see this hydrogen is bonded with oxygen here. Now count the number of elements that are involved in it. 1, 2, 3, 4, 5, 6. So when this intramolecular hydrogen bonding is possible? When within the molecule the hydrogen is there, which is bonded with most electronegative element, and the hydrogen is going to get bonded to an element which is electronegative, has lone pair of electron, also is smaller in size. Amidst all these things, most important point is that it should be able to form the stable six-membered type of a ring. Only then intramolecular hydrogen bonding is possible.
Ma'am.
Tell me, ma.
And but in like any organic compound, shouldn't the cyclic be the main chain? No?
Student?
If the cyclic like part should be the main chain if it's like carbonic acid part is directly connected to it.
I don't get your question.
I'm like you started from O, right, ma'am?
Hmm.
But like the actual counting, like in the name in nomenclature of it, shouldn't the cyclic part be taken as the main chain first?
See, I mean, I'm talking about, you're talking about this nomenclature?
Yes, ma'am.
Yes. See, I'm having two functional groups here, carboxylic acid as well as OH. And this is a cyclic ring. Okay. Now, your question is if the cyclic ring is having more number of carbon, then won't I say that's a parent chain? But this is just an cyclic ring. It has, what is important? Functional group is important. So, along with functional group, I call it as benzoic acid here. Do you understand?
Okay, ma'am.
Okay. So, to make intramolecular hydrogen bonding, which is important, all these checked boxes are filled, but still among them, what is very important? It should have got formed effective six-membered ring is important here. Okay. So what is the importance about this intermolecular and intramolecular? Consider I'm having this orthonitrophenol. Similarly, I have para-nitrophenol. So what are we trying to understand is that which is going to have more boiling point. If I say more boiling point, can I say it is less volatile?
Yes, ma'am.
So the one which is going to have more boiling point, in other words, which is going to be less volatile here. Check whether they are having the possibility of forming intramolecular hydrogen bonding. Look at this hydrogen bonded with oxygen. Hydrogen bonds with oxygen. Intra is possible. When it is intra, what does it mean? When I'm talking about volatility, I can understand this orthonitrophenol is dissolved in water. In the presence of water, it is available. This species need not do the hydrogen bonding with water. It need not do the hydrogen bonding with water. Instead, it does it with itself. Since it does it with itself, like you people uh, are not forming some chains with someone else. Your hands are tied with your own hand. So you are free enough from others. You need not depend on others. You are not trapped by others. So at a very less temperature is provided to it. Less temperature is provided. What will happen? They can get volatilized. But consider here the distance is too large. Very high distance they have. They cannot form intramolecular hydrogen bonding. Instead, what should have happened? It should form intermolecular hydrogen bonding. This could have made a bond with another nitrophenol, again here as well, another nitrophenol. Correct na?
Yes, ma'am.
So what is this bonding called as? Intermolecular hydrogen bonding. This bonding is called as intermolecular hydrogen bonding. Now what do I understand, ma'am? This molecule is in trap of another molecule. Since it is being trapped, you need to spend much more temperature to volatilize it, isn't it? So I understand more temperature is required here. If more temperature is required, we can understand it is less volatile. That is the importance of intramolecular hydrogen bonding and intermolecular hydrogen bonding. Over ma.
Yes, ma'am.
So this is a concept. Let us understand hydrogen bonding here. Here also you could see this is type para position. Hydrogen bonding is not possible. What if it was in ortho position? OH, C double bond OH. You can see the hydrogen bonding is possible. This is intra, isn't it? That means it will have less boiling point. Akriti, did you understand?
Yes, ma'am.
We are seeing certain examples here. Intramolecular hydrogen bonding shown by nickel DMG complex. So it is a qualitative analysis test for nickel 2 plus ions. So we have a complex reagent called as dimethyl glyoxime. So when you take dimethyl glyoxime and you add it to nickel 2 plus salt containing solution, it will turn into pink in color. Or people also say dark red or pink in color. People also say rosy red. So whenever you want to check whether nickel 2 plus is present in that solution or not, you can add little bit of DMG so that the DMG will form a complex with nickel which is having this color. In what context we are learning about nickel DMG in this hydrogen bonding? Because it shows intramolecular hydrogen bonding here. This is DMG, look at this. Dimethyl and this is oxime. Okay, this is called as oxime here. Dimethyl glyoxime. You will be learning about the structure of glyoxime and all later in coordination of compounds. What's happening? You can see the hydrogen bonding is happening here. Can you see this? Within the molecule.
Yes, ma'am.
Copy the structure.
Done, ma'am.
Okay. So 2 years back, we had a question in the hydrogen bonding that is made by this nickel DMG complex. So this is basically nickel DMG twice. That's the reason we say it is an intramolecular hydrogen bonding which is happening between within itself. Nickel DMG twice. The question was how many intramolecular hydrogen bonding are available? How many are available?
Two, ma'am.
Two. One, two. There are two intramolecular hydrogen bonding that is available in the nickel DMG complex. The next complex that you are seeing here is chloral hydrate. It's called as chloral hydrate. CCl3CHO is called as chloral. When it is chloral hydrate, the CCl3CHOH twice. Chloral hydrate. Look at this CCl3 here, COH, OH. Wait, can you see this? CCl3, CHOH twice, correct? So I have one OH here, another OH here, and hydrogen is here. Now the question is, what kind of hydrogen bonding is available here? You can see H is going for an high chlorine here, H goes for an chlorine here. So intramolecular hydrogen bonding. Ma'am, you mentioned that chlorine cannot do effective hydrogen bonding. Yes, it cannot do effective hydrogen bonding. That doesn't mean it can't do hydrogen bonding. It is doing intramolecular hydrogen bonding. Chloral hydrate is used as a sedative. What is sedative?
Sleeping medicine.
Sleep medicine. Correct. We are discussing a little bit about this volume of ice and volume of water, its density, when it be more and all. When I'm talking about this water, you know very well at 4 degrees Celsius only, density of water is at maximum. You say the density of water is 1 gram per ml, right? But this can be exhibited by water only at exactly 4 degrees Celsius. When you talk normal water, it is not 1, it is less than that only. So, what happens here? When I'm talking about this ice versus water, the first point is that the volume occupied by ice is greater than the volume occupied by the water. You are going to take this ice tray, fill it with water till the brim of it. Exactly till the brim you have filled it. Now place it in the freezer and take it. What do you find? You find the ice has overwhelmed its surface, correct?
Yes, ma'am.
Yes. You took water, water is solidifying. So when something is solidifying, you can understand the volume contraction is happening. So if the volume contraction has happened, actually the ice cube formed should be less in volume than the water itself. That's the logic. But what we see conversely, alternatively, we see ice volume is more than water volume. Correct, Appa?
Yes, ma'am.
Now, why this has happened? See, consider the liquid water. The energy of it is quite high when you compare with solid ice. So, when the water molecules are making hydrogen bonding within themselves, okay. So, this water is having more energy here. So, it breaks off with this energy. With this energy, it breaks off little bit of bonds. So they can come close with each other. In liquid water, I'm saying. I repeat, when you're looking at the states of matter, gas has more energy, followed by liquid, followed by solid. This is with respect to energy of the molecules. So in liquid form, as it has more energy, what it does is that as a water molecule is making the hydrogen bonding with another water molecules like this, it has some energy so that it can break this bond and it can come close with each other. But in the case of solid ice, it's not like that. It takes a fixed position here. This hydrogen bonds with oxygen, this hydrogen bonds with oxygen, oxygen, and hydrogen. So with the coordination number of 4, coordination number means how many bonds are made by them. Say the oxygen, you can see it is interacting from with the 4 sides of hydrogen. So they're fixed there and rigid. Because of this rigidity, just by that same position, it gets crystallized. It becomes ice. Now, when it is happening, what happens is that in between this water molecule, lot of space is also there. In between this water molecule, when they are getting bonded with each other, lots of space is there. That solves the first question. Density is equal to mass by volume, right? So I say its space is there. That means its volume is more. First part of question is over. Why volume is more? Because it is fixed in fixed position itself. It is crystallizing. So it's crystallizing. There are a lot of space in between them. That makes it to them to have higher volume. As they have higher volume, now let us compare the density. We can see density is inversely proportional to volume. That is the reason why you are making ice out of water only. But that ice is less dense than water. It floats on water itself. Understood?
Yes, ma'am.
So 2 points we covered. First point is that why do you think volume of ice occupied by the ice is more than the volume occupied by water? Second point is that why do you think ice is floating on water? Why do you think its density is low? Because the volume occupied by it is more. So the density became less. Now we started this question with a point that at 4 degrees Celsius, water shows a maximum density. At 4 degrees Celsius, it's still liquid only, isn't it? It has not got solidified. Step up.
Yes, ma'am.
So till 4, exactly at 4 degrees Celsius, very effective intermolecular hydrogen bonding is existing. That makes its density higher. After this 4 degrees Celsius, either you are going this way or this way, this bond starts breaking. That is the reason why the density decreases. Okay, the next one. So in the case of alkali metal, and I have alkali metal like sodium, potassium, something like that, they also form this hydrogen fluorides. You can see the dimerization is happening here. HF twice. Next one. Due to this hydrogen bonding, carboxylic acid leads to dimerization. Dimerization means they are becoming just double of themselves. So consider I am having carboxylic acid RC double bond OOH. Remember we are talking in the gaseous state. Even if it is liquid state, in non-polar solvent it happens. Similarly here I am having C double bond O, OH and R. You can see the hydrogen bonding is happening. So we say it is getting dimerized.
None, none.
The next point. What else is important about this hydrogen bonding? Very significant part of hydrogen bonding tells us about the boiling point and the solubility. So if you think something is soluble in water, it is well understood that there is a chance of hydrogen bonding that has happened. Solubility in polar solvents like water is due to hydrogen bonding. Solubility in polar solvents like water is due to hydrogen bonding. So we can say like dissolves like. If it is polar, it will get dissolved in polar solvents only. Okay. Now let's go for other applications of hydrogen bonding. H2O is a liquid, while H2S is a gas. The hydrate of oxygen, very immediate member of oxygen's family is sulfur. This is a liquid, but this is a gas. Because oxygen can go for effective hydrogen bonding here. That is the reason why it is liquid. If it is going for intermolecular hydrogen bonding, we know very well it will have more boiling point, right? So it exists as liquid, but H2S cannot do effective hydrogen bonding. So only it exists as gas. Understood?
Yes, ma'am.
Next one, methane cannot form hydrogen bonds, but CH3CN can show how. In methane, the hydrogen is getting bonded with just carbon, where the hydrogen bonding cannot happen. But what about CH3CN, ma'am? Here also hydrogen is bonded with carbon only, but it is also carbon is bonded with cyanide. Cyanide is a strong electron withdrawing group. So what happens? It keeps pulling the electron towards it like this. Because of that, this hydrogen feels electropositive. It definitely needs electron. So now it goes for hydrogen bonding. Boiling point of cyanide versus isocyanide. This is cyanide, C triple bond and the nitrogen is having lone pair. Okay. This is isocyanide. The nitrogen has got how many bonds nitrogen has made now? How many bonds?
Four, ma'am.
Four bonds. If it has made four bonds, will it have lone pair?
No, ma'am.
No lone pair. So because it is having no lone pair, how can some hydrogen come and bond with it? It can't bond with it, isn't it? So it will be having less boiling point. Am I correct? But what about here? Nitrogen is making only three bonds. Nitrogen still has lone pair. So it can form hydrogen bonding. Therefore, it has more boiling point. Similarly, as I said, it is making hydrogen bonds. They are also soluble. Next one is solubility of primary secondary and tertiary amines. Amines means the which is having this NH2 group. If this nitrogen is bonded with only one R, then I call it as primary amine. If the amine is bonded with nitrogen is bonded with two R's, R2NH, then I call it secondary amine. If it is bonded with three R, then I call it tertiary amine. Okay. So in all the cases, you can see the hydrogen bonding is possibility is there. Am I right or not?
Yes, ma'am.
Yes. So the hydrogen of water can come for bonding with nitrogen because nitrogen has lone pair. Similarly, if I'm having this, let me say R3 NH is there, R2 NH is there. This hydrogen is bonded with nitrogen. Can it go for hydrogen bonding?
Yes, ma'am.
Yes, that is a possibility. So lower aliphatic amines are soluble in water. Lower aliphatic amines are soluble in water. But when I'm comparing the boiling point order, since the primary amine is having two hydrogens, it can do extensive hydrogen bonding, isn't it? More is the hydrogen bonding, more is the boiling point. Primary will be greater than secondary, greater than tertiary. Order of boiling point. Over, ma?
Done, ma'am.
Right. So we completed hydrogen bonding. Now we are moving on to weak forces of attraction. Not just this, we did ionic bond, we did covalent bond, we did coordinate covalent bond. Now only these type of interactions are there? No. We have much more interactions and they are weaker basically. Shall we start? Interactions are called as weak interactions. So we're going to learn about what are these weak interactions, in what way they are insignificantly helping us. The first type of interaction is called as ion dipole interaction. Take the word ion will be there and there will be a dipole. Consider I take NaCl, I put it in water. What do you expect?
Release ions, ma'am.
Hmm? What do you expect, Ra? NaCl is an ionic solid, isn't it? In the
Yes,
presence
ma'am.
of water, what would have happened? It should have got dissociated as Na plus and Cl
Yes,
minus,
ma'am.
right? So this is an ion. Now what would happen? Water is there, which is a dipole. Is it a dipole? Is water a dipole? Is water a dipole or not?
Yes, ma'am.
What do you mean by dipole? Which is having both the charges. That is called dipole. So now what happens? This oxygen is electronegative here. You can see it is carrying negative charge. Sodium is plus. So opposite charge would attract, no? So now I can see there is an ion dipole interaction has happened. Now, whenever you see something is getting soluble in water, this interaction only enables them to get soluble. With this interaction only they are becoming soluble. So this is the force for hydration. This is responsible force for hydration. Which force? Ion dipole interaction is important, or this defines the hydration. What is hydration? Covering something with water. When water is surrounding the molecule, we call it as hydration. Now, what are the things that influences it? Number one, size of the ion. Only if the ion is very small, there can be effective interaction. Number two, charge on the ion. If it is having too much of positive charge, definitely oxygen will love to attract it because it is electronegative. Can you see this? It is having this electronegativity and this is electropositivity. So they would interact. Dipole moment of the polar molecule. It should be a polar molecule definitely. All these things influences the ion dipole interaction.
Done, ma'am.
The next one, dipole-dipole interaction. What is this dipole-dipole? That means both are dipolar. They did not have characteristic ions and all. They are dipolar. In the previous example, we had Na plus that was interacting with a dipole. In this example, both are dipolar. HF is there, HF is there. Are they dipolar? Yes, because they can develop charges between them, H plus and F minus. So
Yes,
now
ma'am.
you can see they are getting interacted here. This force is responsible for liquefaction of gas. If you see people are liquefying the gas, then this force is very much responsible here.
Done, ma'am.
Next one is ion induced dipole. Take the word. There is an ion which is inducing dipolar nature in a non-polar molecule. Look at this. What induce means? Something is making it, triggering it to do that. I take an ion, could be Na plus, K plus, anything it could be. And the ion is inducing a dipole on the non-polar molecule. Consider I have noble gas. I have a noble gas, xenon, argon, whatever. An ion is coming close with it. It is inducing that polar nature in it. This is called as ion induced dipole. Okay. The next one. Dipole induced dipole. Ma'am, that is a dipole, ma'am. Look at this molecule. HCl is a dipole molecule? Yes. It is inducing a dipole nature in a homomolecule species. Look at the change here. previous time an ion was inducing a dipole. Now what is inducing a dipole? Dipole is inducing a dipole here. Look at this chlorine here. Both are chlorine. Cl2. Will Cl2 molecule be polar or non-polar?
Polar, ma'am.
Right. Cl2 da.
Unpolar, ma'am.
Non-polar na both are chlorine. Now why do you want to have charge separation there? Both are chlorine only. This is inducing it. There is a dipole which is coming. HCl. HCl is having the charge separation. So what is it doing?
Yes,
It is
ma'am.
polarizing a non-polar molecule. The last one, instantaneous dipole. What is this instantaneous dipole? Consider I am having noble gases, hydrogen, oxygen, chlorine, whatever it is, gases basically. So let me take hydrogen gas itself. Okay, H2. So I know this hydrogen with one hydrogen is available. It is having one electron. Here there is another hydrogen which is having, let me say, take example of xenon. That would be still more comfortable. Xenon. Okay. So I have a nucleus here. It also has nucleus. This also has electron cloud. Instantaneously, momentarily, rarest of the case, what could happen is that both the electronic cloud, this electronic cloud may go to one part. Can you see this? The nucleus is here. The positive, you can see both the positive nucleuses are taking at the same part of this atom. Can you see this? That means the electrons are momentarily at the other side. Can you understand this?
Yes, ma'am.
Usually, when you write an atom, you say nucleus is there, electron is like this, evenly distributed. But you can see there is an uneven distribution in the electron here. One part becomes positive, the other part becomes negative. This is called as instantaneous dipole. So when you see this hydrogen, oxygen, or chlorine in liquid form or in solid form, this interactive force is responsible for that. Okay.
Yes, ma'am.
The last force is called London forces, which is basically called as van der Waals forces, which happens between the gases. So what we have written is in the order, decreasing order of their interactions. So they themselves are weak force of interaction only. Among them, ion dipole is stronger, followed by dipole dipole, followed by ion induced dipole, dipole induced dipole, instantaneous dipole, and the last one is London forces.